returns with a further instalment of Henry Chips Channon's diaries.
Oh, no.
1938 to 1943. Let's talk. Mr. Rigby will talk on the Riemann hypothesis.
Oh.
Thank you very much, Headmaster. I hope you're all paying attention. You've got your exercise books out. I've noticed that in all the talks I've been to, there's been things on photography and architecture and the stones of the southwest. We've not had much actual science. So I thought we'll change that and have a bit of pure science, a bit of pure maths. Let me first of all credentialise myself. I have a grade A GCSE, and that's it. In maths, it's only in maths is the only grade A I achieved. I did take the A level. I say I took the A level. I went in for the A level, but there were several associations at that time that distracted me. There was Association Football, the Conservative Association, and associations with young ladies there in the Young Conservatives over ping pong and cider, and I didn't do too well. But in later years, I've picked up maths again because I think it's an absolutely great thing and quite exciting. But I'm not going to give you all maths. I'm going to give you a bit of history as well about Mr. Riemann, and hopefully this clicker works. So the talk is Mr. Riemann, his famous hypothesis, and why it's important. My name's Mr. Rigby. You can call me Sir if you need to ask a question. You know what the form is. So by the end of today, these are your learning objectives for today's lesson. You'll be able to tell us a bit about Bernard Riemann himself, explain his famous hypothesis at the basic level, explain the implications of the hypothesis, if it's false and if it's true. You'll know that the number -1/12 is a really good number for striking up a conversation with a mathematician. Strange looks if you try and strike up a conversation about it with anybody else. You know how to win £1 million, $1 million actually, by finding just one number. So exercise books out, and we'll crack on. Oh, terms and conditions apply for this 1 million, which I should come on to. So we'll crack on. So Bernard Riemann himself, there he is. He was born in the year of the first photographic plate was produced in 1826, which is why there's no pictures of the younger Bernard Riemann. He was born in what was then the Kingdom of Hanover, obviously now Germany, 17th of September. Second of 6 children. Father was a Protestant Lutheran pastor, and Christianity is a big thing in his life, as we'll find out. From very early on, like the age of 5 or 6, everyone said, that Bernard fella's he's quite good at sums, isn't he? And by the sort of age of 10, 11, he was doing advanced stuff that most other people do at age 18, 19, 20. He was also very quiet, timid, subdued, couldn't really get a word out of him. So he was very quiet and timid, but very good at maths, probably the inverse of most members of the New Sheridan Club, who were quite noisy and probably quite crap at maths most days. But anyway, age 19, he went to live with his grandmother, who lived near the University of Göttingen, and he went there to study theology, join the family business, become a pastor himself. While he was there, very, very early on, he decided to do a bit of maths on the side. Under a chap called Carl Friedrich Gauss, who is a famous mathematician in his own right. About a year after he went to Göttingen, he went off to the University of Berlin, Chairman, and then went back.
It's a quiz night joke.
It is a quiz night joke. Yes, every quiz has to have the answer Berlin somewhere for the chairman's benefit. That, by the way, is Carl Friedrich Gauss, who was Bernard's tutor early on. Both of them, I think, to answer the question, chap or not chap, probably chap. He did a lot of groundbreaking work in a lot of areas, geometry and all sorts of things, and he delivered one paper, and only one paper, in the area of number theory. and this is a short paper, 9 pages long, on the zeta function and prime numbers, and that's what we're going to be coming on to. He married Elise Koch in June 1862, and they had a daughter in December that year. You don't need an advanced degree in mathematics to work out what may have gone on there. He actually started suffering from bad colds late in 1862, and a few times he went off to Italy to try and recover. In 1866, his last trip to Italy, he went because there were various battles on the streets between the Hanoverians and the Prussians, and he died in Italy in that year, aged 39. One of the tragedies is he never published his notes or any unfinished papers or unfinished works. And when he died, his housekeeper burnt the lot. So who knows what may have been discovered. So that's a bit about the history and the man himself. And now the maths bit. Turner, you paying attention back there? Good. Thank you.
Sir, he hit me. Sir, please. I'll be excused.
So, things you'll need to know, things I've assumed you probably understand. Numbers and counting. The negative numbers. Straightforward stuff. Prime numbers. We'll come on to a bit about prime numbers. This is what underpins a lot of this. Adding up, taking away, multiplying, dividing. Getting a bit more complicated now. Knowing that 2 to the power of 3 equals 8, because the 3 is the number of times you multiply 2 by itself to get to 8. 2 times 2 times 2, 8. And then you've got the other side of that equation, roots. So for example, the 4th root of 81 is asking the question, what do you need to multiply by itself 4 times to get to 81? And the answer is 3, because 3 times 3 times 3 times 3. And also you need to know that pi is to do with something to do with circles. And that's it. Does anyone need a primer, a refresher on any of those topics? Otherwise we'll sort of... Yes, sure.
So why is 1 the first number?
Why is number, or is it the first number? Is it?
Or is it 0, sir?
Well, good question. Is it minus infinity? We'll come on to all these questions later on.
Go on, get the logarithms out.
Well, there are
You work it out with a pencil.
associated with all of this is logarithms, but I've ignored all of that. So I thought that was a step too far. So we are going to keep it. We are going to keep it fairly simple. So the paper, the 9-page paper that Riemann posted, was actually all about prime numbers. So prime numbers are things that can be divided by themselves and only themselves and the number 1 to leave another whole number. So 37 is a prime number. You can't find another number you can divide 37 by to get a nice even answer. But 999 isn't a prime number. You can divide that by 9 and 111 and 3 and all sorts of things. It's been known since the time of the Greeks and the Egyptians, in fact, that there are infinitely many prime numbers. You go on forever and you keep finding prime numbers. They never stop. There's always a prime number to go. This is where it gets a bit tricky. Every whole number is either a prime number itself, or you can express it as by multiplying other prime numbers together. So back to our 999 earlier, that could be expressed as 3 times 3 times 3 times 37. Maybe it's a 3 up there. No, I haven't. That is right. 3 times 3 times 3 times 37. Any number you can think of, you can say it's either prime itself, or we can find other primes, which when we multiply them together, give you the answer you first thought of. Very massive numbers, finding out what the primes that make it up can be quite tricky. And this underpins our modern means of encryption. We'll come on to that. The gaps between prime numbers. So the first few gaps, between 2 and 3, there's a gap of 1. Between 3 and 5, there's a gap of 2. And by the time you get to sort of 1,000, the gaps are getting quite big. There's sort of, maybe 5, 10, 15, 20 numbers in between the primes. But sometimes you can go 1,000 numbers without encountering a prime number, and then you get 2 at once, sort of 2 consecutive ones. It looks like they're fairly randomly spread.
Like tube strikes.
A bit like it. Naught and a trillion. There's a formula that tells you roughly how many that is. And what the Riemann hypothesis is about is it tells us how good that approximation is. We'll come on to why that's quite important. Everybody still with us?
Yeah.
Good.
Sorry, what was that again?
So there are things called series, long strings of things that we add up or take away. So here's a series. It goes 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 and so on. And here's another series. And this goes 1 and a half and a quarter and an eighth and a 16th. And here's yet another series. 1 plus a half plus a third plus a quarter plus a fifth plus a sixth. And series generally fall into one of two categories. And keep adding it up. It's not going to get any smaller. It's not going to hone in on a number. Whereas this one here, 1 plus a half plus a quarter plus an eighth, does actually hone in on an answer. Anyone want to hazard a guess as to what number that hones in on? Turner, well done. Have a house point. So effectively, every time you add another number on this, you're just getting closer and closer and closer to the number 2. This one at the bottom here is, let's just click on that. That's convergent. It converges, it hones in on an answer. And here's the final one I'm going to talk about, which is called the harmonic series, which is 1 plus a half plus a third plus a quarter plus a fifth plus etc. etc. Anyone like to hazard a guess as to whether that blows up in your face and goes off to infinity? Not you. Whether it blows up and goes off to infinity or whether it hones in on a final answer. Go on then.
I believe it's divergent.
It is divergent, which is a bit counterintuitive, but let me tell you how slowly it diverges. Suppose you took the first million of these, a seventh plus an eighth, all the way up to 1 million. By the time you've added all that lot up, you only got up to the number 14. You add them all up. If you do the first billion, you get to 23.7. You do the first trillion, you get to 30.6. It's incredibly slow, but it does eventually blow up to infinity in your face. And that's important stuff for what we're going to come on to. So here's where we get to the really important bit. So there's this series here. So this is 1 divided by the square of 1, or 1 over 1, plus 1 divided by the square of 2, plus 1 divided by the square of 2. So it's basically 1 plus a quarter, plus a ninth, plus a 16th, plus a 25th, 36th, 49th, etc. And this is the subject of something called the Basel Problem, named after the town in Switzerland, and was solved by this chap here, Leonhard Euler. It was about 80 years before Riemann. And they'd known for a long time, hopefully fairly intuitive, that this hones in on a particular answer. But nobody knew quite what that answer was. And Leonhard Euler, he solved it. And the answer is pi squared over 6. So all of a sudden we've got these numbers here that seem to have nothing, that have nothing at all to do with circles, and then we've got this sort of thing to do with circles is the answer. And he solved it for a few of these others. So you can have 1 over 1 to the power of 4 plus 1 over 2 to the power of 4 plus 1 to the power of 4, and that was pi to the power of 4 over 90, I think. And he sort of solved these sorts of things, where it's convergent, where the sum looked like this. And then Riemann came along 80 years later, and he took it up a notch. And he said, well, let's say 1 over 1 to the power of a number plus 1 over 2 to the power of a number, any number you like. And we'll call this the Riemann Zeta function. The words aren't important. The important thing is it's 1 over 1 to the power of something plus 1 over 2 to the power of something, etc. That's how it looks in modern mathematical format. So what this basically says is you can stick in a number s, and there's the s, and you add up what all of this comes to. And what that formula there means is stick an s in and add up all the terms from 1 to infinity that look like 1 over something to the s. And that's the Riemann zeta function. We're not there yet. We've got a bit further. But yeah, this is the sort of the fundamental part, knowing that that is equal to the general term of this, which is basically lots of fractions added up. And this is all very closely related to the gaps between prime numbers and how many prime numbers there are when you get to 1 million, 1 billion and beyond. Any questions so far? Everybody still with us?
In the Zeta function, is S necessarily a positive integer? It could be a real number.
We'll come on to that. Excellent question. Have a house point.
Real or imaginary?
Very good question. We are coming on to that shortly. So, he then took it to another dimension, which is what somebody mentioned earlier. So, a very brief diversion. Quick question. Who's first? What's the square root of 25?
Minus 5.
Minus 5.
Well, yes, you said 5, only half house point. Correct over here. The answer is, it could be plus 5, and it could be minus 5. Because if you take a minus number and multiply it by itself, you get a positive number. So plus 5 times plus 5 is 25, as is minus 5 times minus 5. But then mathematicians had a bit of a problem, because there wasn't a way of finding the square root of minus 1, because there's no numbers which, when you multiply them together, give you a minus number, a negative number. So Leonard Euler actually gave this thing a name, but we'll come on to that shortly. So these are all our numbers. There's all the positive numbers going off all the way up to North London, and there's the negative numbers going all the way down to Brighton and beyond. And there's no number on that line that's the square root of minus. You've got all the other numbers on it. Pi's on there, just after 3, and E and various other constants are all on this line. It's not just integers, it's all the numbers. What they decided to do was, we'll imagine, it's purely imaginary, they made it up to make it easy for themselves. We'll imagine there's a second axis on there. We'll put a thing on it called I. And we'll decide that if ever we have a formula that asks for the square root of 1, we'll decide that's the answer. I for imaginary. We made it up. It makes life easier. And then that goes all the way up and all the way down as well. So you get I, 2i, 3i, all the way to infinity I, and all the way down to minus infinity times I. Imaginary. It's made up. It doesn't exist. But it helps a lot. So you've got these normal real numbers, and you've got these imaginary numbers, but you can combine them. You can say, okay, well, let's put something else on here, and let's say well, that's got 4 real bits and 2 imaginary bits, so we'll call that 4 plus 2i. A real part called 4, and 2 of your imaginary parts. And that's a complex number. Real numbers, imaginary numbers, combination of the two, complex numbers. Who's not with us? Haven't lost the room just yet. Good. We'll get into that bit. But we can also do, with all of these numbers here, 4 plus 2i, we can do all the other stuff with them. We can add them, subtract them, multiply them, divide them. We can have them as the exponents. So instead of a squared, 3 squared, we can have 3 to the power of 4 plus 2i. I haven't calculated it now, but I'm sure you'd all like to get your notebooks out and try and work that one out later when you get home. We could also stick it into our Riemann calculator. Instead of, so if we say that S, and we had 1 squared plus 2 squared plus 3 squared, we could put one of these imaginary numbers on the bottom as well. So we can have 1 to the power of 4, 1 over 1 to the power of 4 plus 2i, etc., all the way up as far as we can possibly go to infinity and beyond, as Mr. Lightyear once said. So into our Riemann calculator, just imagine that's a sort of calculator box. We can stick in any number we like. We can stick in the number 10, we can stick in the number minus 3i, we can stick in the number 4 plus 2i, and we'll get an answer. So, brief recap. We've seen 1 over all of these squares. We've seen 1 over all of these, whether they're squares or cubes or tens or millions. And we've got these 1 over 1 to the power of complex numbers or imaginary numbers. This is about as complicated as it gets. So, I'll put our little Riemann calculator box down there. And the big question is, what numbers can we put into this box such that out the other end we get 0? Now, this is the number plane that we saw earlier, with our real numbers and our imaginary numbers and our complex numbers on them. And for all the numbers, why isn't this clicking? For all the numbers above 1, not including 1, but all the numbers above 1, when you put those into this, you get a nice convergent answer. For all these other ones, it diverges and blows off to infinity. But there were some ways around that. I'm not going to explain what analytic continuation is, but it's basically a bit of mathematical jiggery-pokery, which you can look up in your own time, that means they can take the answers there and sort of reflect them. It's really complicated to explain into all the other numbers as well, so that you do get actual answers over here and not infinities, because no one likes infinities. You can't do sums with them. It all breaks down and goes a bit pear-shaped.
So what about Aleph 1?
What about Aleph 1?
And functions and functionals?
Yes, good.
Because
good.
there are many infinities set.
There are. Well, there's an infinite number of infinities. See me afterwards. So now we've got this. We've got all of those ones over there, whereby if we chuck them into our Riemann calculator, turn the handle, press enter, we're going to get an answer out. We didn't have them over here, but with a bit of mathematical jiggery-pokery, yes, we do get an answer. It's not the actual answer, but it's something that represents the answer, and I'll come on to how weird that gets in a minute. So Riemann said, well, let's find where they add up to 0. And he found them straight away. -2, -4, -6, -8, minus any negative number, plug it into the machine, crank the handle, press the enter button, you're going to get 0. Trivial stuff, and in fact these are called trivial zeros. They're too easy. We want the hard stuff. And the hard stuff is in this band here. It's been proven that anything else that ends up with a 0, when you plug any number into here, so if we plugged in -3i, sorry, if you plug in half minus 3i, if we plug that into there, we know that we get an answer out. And it's been proven that in that red line is where all the other 0 answers lie. It's also been proven they all lie incredibly close to this line here, where the real part of this complex number is a half. So everything on that line, the real part is a half, the complex part, sorry, the imaginary part is something else. And the Riemann hypothesis basically says this. These are the trivial ones. All the non-trivial ones lie on that critical line, where the real part, this line here, the real numbers, is exactly a half. And if there are some that aren't on that line, well, then the Riemann hypothesis is false. And they've searched. And they've searched for decades. And they've searched the first several trillion numbers and haven't found one yet where the answer, when you plug it into here, isn't 0. They're pretty damn sure there aren't any. But it's not proven. That's why it's a hypothesis. And remember, all this is related very closely to prime numbers. And that's where we get on to Who Wants to Be a Millionaire? So there's a mathematical institute. It was actually founded in Peterborough, in North America, not that Peterborough, the other Peterborough, by the Clay family, called the Clay Mathematics Institute. And they set a number of problems at the start of the millennium, and this is one of them. And if you can prove this, or disprove it, we'll give you £1 million. Actually, what they said is, if you can prove that all the zeros lie on here, we'll give you £1 million. If you can find one counter-example, we'll give you some of it, not necessarily $1 million, we'll talk about it. That's the sort of terms and conditions apply. I think they'd be hard pushed. It's just as important to know that this is true or whether it's false. It'd be great if it's true. But if it's false, it would also be incredibly important to know. You go down in mathematical infamy if you found that number. You know, you'd be hated by so many mathematicians.
And businesses.
And we'll come on to these right. So, if you find, if that red dot there, when you plug it into here, gives you 0, oh dear, good for you, you'll be famous, you'll get part of £1,000,000, but a lot of maths will be turned on
Sir,
its
won't
head.
you have broken a lot of physics as well, sir?
We'll come on to that, very good indeed. Maths underpins pretty much everything. There's also a very strange thing that happens with some of this analytic continuation. I've put in red there, -1. And I'll come on to why that gives you a strange answer. So, if we plug -1 in to our Riemann calculator box, we get 1 over 1 to the power of -1 plus 1 over 2 to the power of -1, all the way up to infinity. And that equals, it's quite a trivial mathematical sum, equals 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way along. Now, when you plug this in to the, when you plug in -1 into the Riemann zeta function, or the analytic continuation of the Riemann zeta function, you end up with -12. Now, it should be clear to you, it was clear to me, that if you add up all the numbers, 1 plus 2 plus 3 plus 4 plus 5, all the way to infinity, you almost certainly don't get -12. But there are times in quantum mechanics where you do get 1 plus 2 plus 3 plus 4, and you have to find the answer, put that into your formula, and then do more things with that. And if you put -12 in instead of infinity, you get the answer you expected, or the answer you observed. So there's definitely some relationship between 1 plus 2 plus 3 plus 4 all the way to infinity and the number -1/12. I'll let you ponder that.
Don't talk about renormalisation theory in quantum mechanics, please.
I won't. Just because you said. Now, a lot of this, there are lots of other proofs. A lot of other ways of explaining that 1 plus 2 plus 3 plus 4 equals -12. And here's sort of part of one of them. Suppose we've got this series here, 1 plus 1, 1 minus 1 plus 1 minus 1 plus 1 minus 1, all the way to infinity. What does that add up to? So let's think, if we took the first two numbers, 1 minus 1, 0. Brilliant. Take the first three numbers, 1 minus 1 plus 1, we've got 1. Take the first four numbers, we end up with a 0 again. The first five numbers, we end up with a 1 again. So I guess the answer is, it depends what the last term is, as to whether this adds up to 0 or 1. But there's no last term, it goes on forever. And some of the proofs, some of the proofs, the 1 plus 2 plus 3 plus 4 equals 1 to 12, basically frig it a bit. So well, let's split the difference and call it a half. And if you do that, then you can actually show that this does equal that. Of course, that doesn't equal that. But it's fascinating that it actually works in the real quantum mechanics world. All of that stuff. Why do we care? Why do? Well, I'll give you three reasons. It's like Everest. It's because it's there. We want to. This problem's been around for sort of 160, 170 years. We'd like to solve it. It would be fantastic if we could. Second reason, because it's fun. Trust me. I got into this again after my GCSE, so GCE, in fact it was then, after my GCE, and YouTube was just starting up, and there's great YouTube channels all about maths, short videos, 5, 10, 15 minutes long, and spend many an evening watching some of these, bringing myself up to speed with, and reminding myself of things that I'd forgotten that I learned back at school. But there are other reasons why it matters. There are hundreds of maths papers, some of them quite important ones, that start off with the words, assuming the Riemann hypothesis is true, then all of this other stuff I'm saying is fantastic. But they aren't proven because they're all subject to this
It's not
thing.
equal to MP.
Oh, is it? And
Oh yeah, it actually
P
comes
versus
down to that.
NP
If you
comes down to that.
disprove the Riemann hypothesis, you've actually demonstrated that P equals NP, and therefore there are no insoluble problems.
So maybe next time I'll do the P versus NP problem. Yes. I think I shan't. I think I shan't. I think I'll go back to talking about Tunbridge Wells on the next one. If it's false, we'd have to question a lot of what we know about prime numbers. And prime numbers are these building blocks, and they really help us out. And a lot of what we know about prime numbers determines our encryption systems. So if you send an email and it's encrypted, if you do a bank transfer, if you use your credit card at the bar, this is based on the fact that NatWest gives you a number that's massively long, that's 780 characters long. It says, I bet you can't work out what the prime numbers are that make this up, and nobody can. If they could, NatWest wouldn't be able to encrypt anything. So it's really, really important that what we know about prime numbers turns out to be true. If the Riemann hypothesis turns out to be false, well, we're all in a bit of trouble. So, before I wrap up, any questions, anything people want me to go over? There's something funny, Harley. You want to share the joke with the class?
No, sir. I was just enjoying your lecture so much. It made me smile, sir. I didn't quite get the proof of why 1 plus n to infinity is the same as minus 1 over 12.
It's not,
Okay.
is the answer. But if you use some mathematical jiggery-pokery, you can make it look like.
Right.
So there's some relation between minus a 12th and the sum of all the numbers. Well, it clearly isn't the sum of all the numbers, because you don't even get to any minus numbers. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 5 is 15. You don't go anywhere near any fractions, let alone any minus numbers. But there's some relationship there somewhere, as I said, because it's shown by quantum mechanics. Yes?
One might say that what they've done is technically they've renormalised it. Imagine you look into a mirror, and we all know you see your reflection in the mirror. Left is right, right is left, and that's why, trying to shave just here is tricky, because it's the wrong way in the mirror when I look at it. Now with renormalisation, what you've done is you've put on a different pair of spectacles, and you said, right, I want to see this in the renormalised light, in the yellow light, and that's effectively what's happened. They've applied a load of mathematics to turn it into that.
I wasn't going to go into this. So, Turner, have you got your hand up?
Yeah, so the sequence of divisors in the Riemann function is the ordinal counting. Are there other sequences where you have sequences of those ordinals at different values? So sort of rather than 1, 2, 3, 4, 5,
Yeah.
Sort of 1, 3, 5, 7.
You can have any series. You can have any series you like, as long as you can describe it.
Other common series are often called, if you look at them, Basel functions.
Right.
The Basel functions J0. That's the first one. There's Jn for many Basel functions. N, T, and
Yeah. That's exactly what I was going to say, and I'm glad you mentioned it.
was actually asleep.
Oh, there.
Resting his eyes. Just musing on the.
Any other? Oh, there we go.
Just trying to figure it out. So you concentrate, close your eyes. You just what's going to be tonight?
Oh, yes, go
I'm
on.
going to be a tricky writer now.
Go on then.
If we go back to your slide where you had the pictures of, on the vertical axis, on the imaginary axis of the half, right, and we saw the dots on there, the red dots.
This one here?
So the dots, excellent. Do you have any comment that essentially the reapplication of the Basel function is related to fractals?
That's the next lesson, so I'm glad you.
That'll be a next minute.
Next time now. We shall come on to that. Now, what I would say to you is, nobody likes a smart ass. And
Yes, but I have pictures, sir.
so I'm sure keep them to yourselves.
No, these are safe for work.
So where were we? Let's sort of go back through this minus the 12th business. Why does it matter? Our encryption is based on it. Any more questions before we Say class dismissed.
So
Turner.
that encryption fundamentally, what threat does quantum have, quantum computing?
Well, there are sort of two competing. This is sort of going slightly off topic, but there are sort of two, as far as I'm aware, and cryptography is my job, by the way, or part of my job. There are sort of two competing things happening at once. There's quantum computing, which can do loads and loads of calculations all at once and find things very easily that ordinary linear programming can't.
Like Excel, you
A bit like Excel, yeah.
Like that.
But there's also quantum cryptography, which is based on the fact that you can have two particles that both move at exactly the same time. You move one, the other one moves, and entanglement. Oh, yes. I'm trying to keep it light. But there's that. There's also the sort of the very effect of quantum particles, whereas if you observe them, they change. So you know if someone's spied upon your quantum communication, and therefore you know not to trust it and that sort of thing. So I think these two, quantum computing and quantum cryptography, are sort of in a sort of arms race against each other. Yes, it will have to be resolved, or else we're all back to the dark ages of the 1970s.
Aside,
Well, it won't be long.
this also relates to Shannon's theory of information and also entropy.
Not that Shannon.
Oh, not that shit.
No,
No,
different
as
Shannon.
in not the rock, it's the famous mathematician Shannon in the early 1920s, and his idea of complexity limits and so forth, which also underpin the idea of Kolmogorov complexity and computational theory. Which is why this is crucial to P equals NP.
I think we
Because it's
should.
relating to ability to compute, and you're talking about quantum computers. Precisely so.
I see a lecture by you coming on at the club one day.
Bring your own pillows.
Yes.